Can any continuous function, no matter how complex, be perfectly approximated using simple, well-behaved equations bound by a strict error margin? Looking at Theorem 7.26 in Walter Rudin's Principles of Mathematical Analysis, we find the classical answer. In 1885, Carl Weierstrass proved a landmark result in real analysis. He established that any continuous complex function defined on a closed interval can be uniformly approximated by polynomials. You can always find a polynomial that traces the target function as closely as you need. But modern analysis demands more flexibility. We frequently need to leave the standard real line for abstract topological spaces, or use entirely different families of functions, like trigonometric series, instead of standard polynomials. To do that, we need Marshall-Stone's generalization of the Weierstrass theorem. Stone distills polynomial approximation down to its purest algebraic and topological components. In 1937, Stone realized that the specific arithmetic form of a polynomial, x to the power of n, is actually irrelevant to why the approximation works. The engine driving the approximation is structural. It relies on the algebraic rules the functions obey and the topological compactness of the space they exist within. To understand the mechanics of this theorem, we will systematically deconstruct Rudin's definitions, starting from the foundational sets and building up to the proof itself. To understand the whole, we must first build an abstract ecosystem of functions that play by strict algebraic rules. Rudin begins with definition 7.28, establishing the concept of a function algebra. This defines the exact pool of functions we are allowed to use. As this diagram illustrates, an algebra is a family of functions closed under addition, multiplication, and scalar multiplication. If you add or multiply any two functions in the set, the result is guaranteed to still be inside that set. We then expand this pool by defining its uniform closure. This is the set containing all the limits of uniformly convergent sequences drawn from that original algebra. This brings us to Theorem 7.29, which proves that the uniform closure of an algebra is itself a uniformly closed algebra. This proof matters because it guarantees our pool of limit functions won't lose their predictable algebraic properties when we push them to infinity. We have now established a mathematically sealed environment. We can safely build infinite approximations without breaking the structural rules of our set. Next, the algebra needs the capacity to mimic a target function locally. Definition 7.30 introduces the property of separating points. Geometrically, this means the algebra has enough resolution to distinguish between any two distinct inputs. For any 2 points in the domain, there is a function in the algebra that yields different values for them. It can differentiate between them. We pair this with the vanishes nowhere condition, which ensures our algebra doesn't universally flatline at 0 for any single point in the domain. These two properties lead directly to the interpolation lemma in Theorem 7.31. The mechanical result of this lemma is powerful. Using our algebra, we can construct a function that perfectly hits any two arbitrary values at any two arbitrary points. However, this lemma is strictly local. It only guarantees exactness at those two specific points, telling us nothing about the function's behavior everywhere else. Separating points and vanishing nowhere provides the necessary local control. These conditions extend a 2-point exactness into a global approximation across the entire set. We arrive at the formal Stone-Weierstrass theorem, Theorem 7.3. It states that if an algebra of real continuous functions on a compact set separates points and vanishes nowhere, then the uniform closure of that algebra consists of all real continuous functions on that set. Two critical hypotheses carry the weight here. The domain must be compact, and the functions must be real. Rudin divides the proof into 4 steps. Step 1 proves that if a function is in the uniform closure, its absolute value is also in the uniform closure. The strategic goal here is algebraic manipulation. Once the absolute value is included in the closure, maximum and minimum operators can be expressed through standard algebraic formulas. This animation demonstrates why those operators are necessary. By taking the max or min of two intersecting functions, we can create rigid upper and lower envelopes. Because we can take these maximums and minimums, the algebra behaves topologically like a lattice. It contains these sharp boundaries. Armed with this lattice property, we possess the surgical tools required to take different local approximations and stitch them together. Here is how the global approximation is constructed. We start with our target continuous function, bounded by an allowed error margin, the epsilon tube. We apply the interpolation lemma from earlier to intersect the target function with a local function from our algebra at a single point, x. Because both functions are continuous, this local approximation stays within the epsilon tube for a small open neighborhood around x. Outside that neighborhood, it drifts away. This is where steps 3 and 4 of Rudin's text invoke the vital property of compactness. Compactness guarantees that we don't need infinite local approximations. We can cover the entire domain with a strictly finite number of these valid open neighborhoods. Finally, we apply the lattice operators, the maximums and minimums established in step 1, to this finite collection of local functions. This creates a continuous envelope that tracks the target function within epsilon across the entire domain. Because we combined a finite number of functions using standard algebraic operations, the resulting global envelope is still a valid member of our original algebra. Topological compactness is the bridge. It forces an infinite local problem down to a finite global solution, proving that the algebra is uniformly dense. There is one caveat. Theorem 7.33 addresses what happens when dealing with complex algebras, where the standard Stone-Weierstrass theorem fails. The required fix is that the complex algebra must be self-adjoint. It must be closed under complex conjugation. If a function is in the algebra, its complex conjugate must be there too. Beyond pure analysis, these structural results serve as the foundation for modern applied mathematics. In machine learning, it forms the mathematical bedrock for the Universal Approximation Theorem, proving that neural networks can approximate any continuous function. Looking ahead to Chapter 8, Rudin immediately uses Stone-Weierstrass to establish the foundations of Fourier analysis. Trigonometric polynomials form a self-adjoint algebra that separates points on a circle. Because of this, we know definitively that Fourier series can approximate any continuous periodic function. The Stone-Weierstrass theorem generalizes approximation from the real line and standard polynomials to abstract spaces. It requires only 4 load-bearing pillars: a valid algebra, the ability to separate points, vanishing nowhere, and a compact domain. The theorem demonstrates the convergence of topology, algebra, and analysis into one cohesive geometric argument. If you found this breakdown of Rudin helpful, like and subscribe for more chapter-by-chapter analysis.